In the previous section, we showed how Einstein's particle, or photon description of light, correctly described the photoelectric effect in 1905. However, the particle picture of light did not gain general acceptance until 18 years later, in 1923, when another set of experiments could only be understood within the framework of a particle picture. The American physicist Arthur H. Compton used the photon model to explain his research on the scattering of X-rays by electrons in graphite. X-rays are high-frequency electromagnetic waves, and like visible light, they are composed of photons. The following clip illustrates what happens when an X-ray photon strikes an electron in a piece of graphite. Like two billiard balls colliding on a pool table, the X-ray photon scatters in one direction after the collision, and the electron recoils in another direction. Compton observed that the scattered photon has a frequency f' that is smaller than the frequency f of the incident photon, indicating that the photon loses energy during the collision. In addition, he found that the difference between the two frequencies depends on the angle theta at which the scattered photon leaves the collision. The phenomenon in which an X-ray photon is scattered from an electron, with the scattered photon having a smaller frequency than the incident photon, is called the Compton effect. We model the collision of a photon and a charged particle as a completely elastic collision, so that both linear momentum and kinetic energy are conserved after the collision. The electron is assumed to be at rest before the collision and completely free, i.e. not around an atom in a material, for example. According to the principle of conservation of energy, the energy of the incident photon must be equal to the energy of the scattered photon plus the kinetic energy of the recoiling electron, where the relation E equals hf has been used for the photon energies. It follows then that hf' equals hf minus ke, which shows that the energy and corresponding frequency f' of the scattered photon are less than the energy and frequency of the incident photon, just as Compton observed. Since lambda prime is equal to c over f', the wavelength of the scattered X-rays will be larger than that of the incident X-rays. From the perspective of conservation of linear momentum, we must have the momentum of the incident photon being equal to the momentum of the scattered photon plus the momentum of the recoiling electron. Recall that this is a vector equation, and it requires conservation of linear momentum in both the x and y directions. So how do we write the momentum of a photon? For a regular particle, the momentum is equal to mass times velocity, but a photon is massless and moves at the speed of light. To handle it correctly, we have to use the relativistic equations for the momentum and total energy for any particle that we derived back in Chapter 28. Solving each of these equations for gamma m and setting them equal to each other gives the following. Since a photon travels at the speed of light, we set v is equal to c and write the final expression for the momentum of a photon. This result only applies to a photon and does not apply to a particle with mass, because such a particle cannot travel at the speed of light. And since E is equal to h times f, and c is equal to f times lambda, we derive the following expression that relates the momentum of a photon to its wavelength. Using this expression and the results from the energy and momentum conservation, Compton showed that the difference between the wavelength lambda prime of the scattered photon and the wavelength lambda of the incident photon is related to the scattering angle by the following. In this equation, m is the mass of the electron. The quantity h over mc is called the Compton wavelength of the electron, and it has a value of 2.43 times 10 to the minus 12 meters. Since cosine theta varies between plus 1 and minus 1, the shift lambda prime minus lambda in the wavelength can vary between 0 and 2h over mc, depending on the value of theta, a fact that was observed by Compton. The photoelectric effect and the Compton effect provide compelling evidence that light can exhibit particle-like characteristics attributable to energy packets called photons. But what about the interference phenomenon discussed in Chapter 27, such as Young's double-slit experiment and single-slit diffraction, which demonstrates that light behaves like a wave? Does light have two distinct personalities in which it behaves like a stream of particles in some experiments and like a wave in others? The answer is yes. And physicists now believe that this wave-particle duality is an inherent property of light, indicating that light is a far more interesting and complex phenomenon than just a stream of particles or an electromagnetic wave. In the Compton effect, the electron recoils because it gains some of the photon's momentum. In principle, then, the momentum that photons have can be used to make other objects move. And while a single photon carries a very small momentum, many photons striking an object can have a significant effect on its motion.